Hey, 2003 Mechanics, number 2. We've got a little tray kind of contraption that has mass m, and we're going to drop a little ball of clay onto it. Here's your spring. It was here when it was relaxed. It got stretched this distance d by hanging the tray on it of mass m. And we're going to drop this little ball of clay from a height h above the tray. Alright, so let's see what's involved here. Determine the speed of the clay at the instant it hits the pan. Well, anytime we want to know the speed of things from dropping them, we have a choice. You can do kinematics or you can do energy. I'll sketch those both out for you real quick. So for part A, we're dropping mass m from height h. I'll do the kinematics for you real quick. It's just a vertical problem. So in the vertical direction, we're dropping it with an initial velocity of 0. We would like to know its final velocity. Its acceleration is negative g, in other words 9.8 down, and it's dropping, it's delta y, it's dropping a distance of h. So the question that, the equation that relates those is final velocity squared is equal to initial velocity squared, which is 0, plus 2a delta h. The negatives cancel out, so 2 delta y, which is h. So the final velocity is the square root of 2gh, which is the answer for part A. You could also do energy. You could say that the potential energy is going to be transformed into kinetic energy. So that means it's m g h. I'm using the same letters, the capitals that they use, would turn into 1/2 m times its velocity squared. The m's cancel, you multiply by 2 and take the square root, and you get the same thing. Okay. That's part A, done two different ways. That's the speed of the clay as it hits the pan. Determine the speed of the pan just after the clay strikes it. Well, look, collisions. Anytime two things strike each other, you can be pretty dang sure that you're talking about conservation of momentum. So, momentum is conserved, whether it's an elastic or inelastic collision. Momentum is conserved. Kinetic energy is only conserved if it's inelastic, if they bounce. So here, since momentum is conserved, let's see what that means. That means momentum, which is P, right? Momentum before equals momentum after. Well, before, the only thing that has momentum is the clay dropping, right? And this is its velocity. So it's mass times its velocity is equal to the momentum after is 2m. 2m is the mass of the tray with the mass of the clay stuck to it, right? They're going to move together after the collision. So it'll be 2m mass total times the velocity of the, what do they call it? The velocity of the pan. So I'll call that velocity of the pan. So solving for that, that gives me the velocity of the pan is equal to the square root of 2gh over 2. Since they were the same mass, it shouldn't be any big surprise that it got cut in half when we did that. But you have to show your work. Certainly, or I'm not sure, but I bet there's a point for conservation of momentum there. In part C, determine the period of the simple harmonic motion that ensues. Well, let's see. What are the different considerations here that we need to figure? We need to figure out, this is a mass oscillating on a spring, right? So the period is equal to 2 pi times the square root of m. What's the mass of the whole thing is 2m over k. And I think I've got everything that I need here except for the k. So can we find k? Well, let's see. Back to our original drawing here, when I hung the tray or the pan of mass m on here, it displaced this d, right? That means the gravitational force of this caused a displacement here. That means the gravitational force of the pan is equal to the spring force of the pan pulling back, which means mg is equal to kx, right? Because when you hang the pan on there and it drops a little bit and then it rests because it's just resting there with the spring, that means gravity and the spring force are balanced. So that's what I'm doing here. All right, so let's set that up for this. We know that mg, and m is the mass of the pan, not with the clay on it yet, right? G is equal to k times the distance that it got stretched was that d right there. So k is equal to mg over d. So plugging that in here, that gives me t is equal to 2 pi times the square root of 2m over mg over d. So that gives me 2 pi times the square root of 2d over g. There's the period. All right. Part D. Determine the distance the spring is stretched from its initial unstretched length at the moment the speed of the pan is at a maximum, and then justify your answer. Well, if you think about simple harmonic motion, when is speed at a maximum? Think about that for a second. The maximum speed happens at equilibrium, right, as it passes through equilibrium. So we just need to find the equilibrium point, or in other words, this is going to be at excuse me, this will be at equilibrium when the mass of the clay in the pan have stretched it just to that equilibrium point where gravity and the spring force are balanced. In other words, it's however far it would stretch with this kx. So we want to figure out when the mass is 2m, that's going to be, what's our k from the last one? K is equal to and we're looking for this distance right here. So this is, again, I should probably write this down. This is, we're using the idea that mg is equal to kx at equilibrium. It's the same idea that we used before to find the k. And then the mg's cancel out, so x is just 2d. That, again, that shouldn't be any surprise. It shouldn't be any surprise because when we had mass m hanging on the spring, it got stretched to distance d. When we have mass 2m on the spring, it gets stretched to distance 2d to be at equilibrium. All right. The clay is now removed from the pan, and the pan is returned to equilibrium at the end of the spring. So we're back in this situation. A rubber ball, also of mass m, so now this is a little rubber ball, is dropped from the same height h onto the pan, and after the collision, it's caught in midair before hitting anything else. So we drop it, it bounces off the pan, gets the pan moving, but it doesn't stick, it bounces off. They want to know, indicate below whether the period of the simple harmonic motion is greater than, less than, or the same as it was in part C. Well, let's see. Period is equal to 2 pi is the square root of m over k. Now, this is the period of whatever's in motion. This was 2 pi times the square root of the mass when the lump of clay was stuck to the pan. It was 2m over k, right? And we found the k. And now, since the ball's bouncing off and not sticking, the period's going to be just this, right? The second m, the lump of clay didn't stick. So is it getting bigger or smaller? It is getting smaller. How do we justify our answer? The period is smaller because the mass that's actually in simple harmonic motion is smaller, and period is equal to 2 pi times the square root of m over k, right? So if you decrease the mass, you're going to decrease the period. Right? All right, not too bad.